Hello, and welcome back to the second lesson in our Introduction to Formal Arguments. In this lesson, we'll be going over logical operators and truth tables. In our last lesson, we talked about the type of arguments we'll be looking at in this series, which are deductive arguments, and the type of thing we'll be looking for when we evaluate logical arguments for form, which is validity. Just a reminder, valid arguments have premises that, when true, lead to a conclusion that will also be true. This property is called entailment. When we talk about truth in logic, that's essentially a value. When we test for validity of form, we assume that given premises are true, and that will become more apparent while we do that in a future lesson. We are using sentential logic, so we are using simple sentences as our variables to fit into our forms. Again, this is meant as an introduction to, and not a mastery course, or really even a intermediate course in logic. What is a logical operator? Well, a logical operator, also known as a logical connective, is a way in which two components with specific values interact. It shows the relationship between two concepts in a way that we can establish the truth value of that relationship. We use them every day in language. They're a key factor in how we understand concepts. They're prominent in grammar and syntax. There are many operators, but we'll be focusing on the 5 most common in language: conjunction, disjunction, conditional, biconditional, and negation. These 5 are exhaustive. That means that using the 5 or a combination thereof, you can essentially express the entire possibility of relationships between premises or propositions. In order to understand operators, we'll be using what we call truth tables. And what a truth table is an expression of all the possible combinations of truth values given the propositions contained therein. For instance, this truth table has the variables p and q. Each has a truth value of either true or false. There are 4 possible outcomes. This table shows all the possible combinations of p and q depending on what their truth value would be. When we connect p and q with a logical operator, we're also able to determine the value of the resulting combination. Truth tables are an expression of the way the logical operator functions, and these relationships are typically expressed via a symbol. They don't have a set key, so depending on which resource you're looking at, they may be different symbols, but there will always be a key to let you know to which symbol they are referring. The first operator we'll be looking at is a conjunction. The conjunction is true if and only if both components, known as conjuncts, are true. In language, a conjunction is typically expressed with the word and, but it can also be expressed in different ways. It's the relationship and not the word you're actually looking for. Other words you might see used to denote a conjunction are but, while, or other chronological words that indicate the presence of a conjunction. They have a feature known as the associative property, which means it doesn't matter which side of the operator each conjunct is on, the truth value of the conjunction remains the same. We will be using the phallus symbol, the upward arrow, to denote conjunction. Here you can see on this truth table, if P is true and Q is true, then P and Q is also true. P and Q is false in every other scenario. Let's look at this proposition. Bill and Harry ate cheeseburgers last Tuesday. You'll remember from our last session that we break down this proposition into the simple sentences contained therein. We'll have B equal Bill ate cheeseburgers last Tuesday. H will represent Harry ate cheeseburgers last Tuesday. Once we have those variables, we can insert our operator, the phallus, which represents and, which should translate into our original proposition. To read it out, Bill ate cheeseburgers last Tuesday and Harry ate cheeseburgers last Tuesday. Now, if you look at the truth table, you can see the only way for that sentence to be true is if indeed Bill and Harry both ate cheeseburgers last Tuesday. If either did not, then the entire statement is false. The next logical operator we're looking at is the disjunction. The disjunction is true if at least one of the components, also known as disjuncts, is true. In language, we typically express a disjunction with or. Either is another term that you should look out for, which might denote a disjunction. Just like conjunctions, disjunctions have the associative property. It doesn't matter which side of the operator the variables are on. We use the chalice symbol, the V, to denote disjunction. Here we have another example. Consider the following proposition. Andrea will eat a salad or some chicken for lunch. We draw out the simple sentences. S will stand for Andrea will eat a salad for lunch. C will stand for Andrea will eat some chicken for lunch. Now we can add the operator, the phallus, the or symbol. And it translates into our original proposition. Andrea will eat a salad for lunch, or Andrea will eat some chicken for lunch. We can now see that the proposition S or C is only true if one or the other is true, or both. Our next operator is a conditional. A conditional is true unless the foremost component, called the antecedent, is true, but the latter component, called the consequent, is false. It might seem that this is a little more complex than the other two. The conditional is expressed in language as if, then. Whence, once, and just if can denote a conditional, but you should pay close attention to what statement comes first in order of the things actually happening, not necessarily the first thing in the sentence, when considering a conditional. Unlike the other operators, conditionals do not have the associative property. The antecedent must always remain on the left, and the consequent must stay on the right of the operator. We will use the rightward-facing arrow symbol to denote a conditional. Something interesting about conditionals is that they can indeed be true if both of, well, they are true rather, if both of the components, the antecedent and the consequent, are false. This is the equivalent of saying something along the lines of, I'll eat my shoes when pigs fly. It's a true statement because neither will ever happen. Well, you could potentially eat your shoes. Here's an example of a conditional. Jim will clock out once Gina arrives for her shift. First, we draw out the simple sentences. We have the proposition that Jim will clock out, and we have the proposition Gina arrives for her shift. Let's let them be represented by J and G respectively. Now we add the operator. Remember, we must ask what comes first in order. The thing that happens first must come first in the interpretation. In this instance, what must happen first is Gina must arrive for her shift. So we get if G, then J. This translates into our original proposition and concept. If Gina arrives for her shift, then Jim will clock out. Now you can see that If G, then J is only false when the antecedent is true but the conditional is not. Right? The only way that's going to be false is if Gina shows up and Jim does not clock out. Next we have a biconditional. A biconditional is true only if each of the components have the same truth value. In language, this is expressed as if and only if, but it is the relationship again and not the word that we are actually looking for. The biconditional is logic's identity claim. It says that two concepts are equivalent or dependent on each other. Always and other words that show no variance are indicators for biconditional. A biconditional is essentially two conditional statements with the components flipped. Both components are antecedents and consequence. As a result, biconditionals have the associative property. We will use the double-facing arrow symbol to denote a biconditional. Consider the following proposition. Gladys will set the fine china if and only if it is a holiday. Draw out the simple sentences. G is Gladys sets the fine china, and we'll have H represent it as a holiday. Now add the operator to express the entire concept. G, if and only if H. This should translate into our original proposition. Gladys sets the fine china if and only if it is a holiday. We can now see that G, if and only if H, is true only when G and H have the same truth value. In other words, Gladys doesn't break out the china if it isn't a holiday, but if it's a holiday, Gladys will always set the china. Finally, we have negation. A negation is true if and only if the concept to which it applies is false. In language, this is usually expressed with a not. But there are many different ways to show negation, including specific words for a negated instance. Pay close attention to unprefixes and apostrophe nt contractions, among various others. The negation is the only operator we will use that only applies to one component. We use the tilde symbol to denote negation. Consider the following proposition. Jake will not make it to class on time today. We draw out the simple sentences and we remove the negation. That's always important. It's something left over from our last lesson, and you'll see why now. We draw out the simple sentence, we get J equals J will make it to class on time today. Now we can add the operator to express the entire concept, not J. This should translate into our original proposition, and it might help to use the phrase, it is not the case. It is not the case that J will make it to class on time today. We can now see that not J is true only when J is false. This is likely the most intuitive of the operators. A few further notes. You can have multiple operators in a single premise. We will show you in a future lesson how to use parentheses to denote what the scope of the operators are. So, like I said, a concept we'll touch more on in the next lesson. It might be helpful to remember that while we use variables to demonstrate simple sentences, those variables are placeholders for form. A conditional might serve as one of a conjunction's conjuncts, for example. You may have noticed that you can say something in multiple ways, and it is indeed true that some operators function in a way to provide equivalence. And those equivalencies have rules of their own known as rules of equivalence, which we will cover in our next lesson. Congratulations, you made it to the end of the slideshow. Pat yourself on the back. I'll see you next time.